Hello everyone, my name is Koma Signolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, welcome to another video on momentum. We are continuing with our lessons on momentum, and in this video we will be looking at impulse. We'll be looking at what impulse is and why impulse is important, and we'll be looking at the equation for impulse. Okay, so let's get right to it. So first of all, what is impulse? Okay, so before I actually define impulse, we're going to revisit some concepts that we've already covered. Now, we understand and we know that what we're dealing with, the main topic that we're dealing with here is momentum. Okay, and if you remember, momentum represented by the symbol P is given by the mass of an object times the velocity with which that specific object is traveling. That is the equation that defines momentum, and we looked at examples. We used this equation with a couple of examples, and we gave you practical examples where momentum is used in real life. Okay, now we defined what momentum is. We defined that momentum is the mass of an object times the velocity at which the object is traveling, and then we defined the law of conservation of momentum. Now, if you remember from previous videos, we spoke about the law of conservation of momentum. Okay, law of conservation of linear momentum. Law of conservation of linear momentum. And we said that the linear momentum in an isolated system remains constant. Okay, and we even gave examples of of two cars colliding with each other. We said that if you've got a car and you've got another car, and these cars collide, right? If this is an isolated system, we spoke about how the momentum before collision is going to be equal to the momentum after the collision if this is an isolated system. Now, what is an isolated system? We defined what an isolated system, and we said that an isolated or a closed system, an isolated or a closed system, if you don't want to say isolated, you could say closed. An isolated or a closed system is a system where your Fnet is equal to 0. Okay, where you don't have a net resultant force acting on the bodies involved in the system. Okay, so what is this net force? We went on and said that friction is an example of an external net force that could be applied on the objects in the system, or it could be a person pushing the objects in the system. It's an external applied force. Okay, so if you've got these cars that I drew up here, and there's friction acting between the wheels of the car and the ground, if there's friction, then this friction counts as the Fnet. That's the external net force that is being applied on the system. And therefore, if we've got a frictional force, or we've got someone pushing this vehicle while it's moving, right, then we know that we do not have an isolated or a closed system. Okay, so that's just a recap. That's just a quick recap. We don't have an isolated or a closed system if our net force is equal to some value, right? For us to have an isolated or closed system, our net force, an external applied force, has to be equal to 0. Now, what if we don't have a closed system? What if our system is not closed or not isolated, not closed, or not isolated? Okay, then that obviously means that we have a net external applied force on our bodies. So I'm going to give another example. Let's say you've got a soccer ball, right? And the soccer ball is moving at some velocity. I'm going to call it v1. It's moving at some velocity. Okay, it's on the ground and it's moving at some velocity. Now, while this ball is moving, if somebody comes and kicks this ball while it is moving, pay attention, it was moving to begin with. Someone comes and kicks it while it is moving. What's going to happen? Well, obviously it's going to move faster, right? So then the velocity is going to increase. V1 is going to increase. Okay, so that velocity is going to become bigger. Now, remember what the equation for momentum is. The equation for momentum is P is equal to m times v. Now, if we change the velocity with which the ball is traveling, right? Because we've got a boy here and the soccer ball is moving, even if it isn't moving. Okay, we've got a soccer ball here and this person comes and kicks the ball and changes the ball's velocity. What happens? If the ball's velocity changes, it means that v of the ball changes. If that v changes, then it means the momentum changes, because the v is a part of what makes up the momentum, right? So if the velocity changes, then it means that the momentum changes. So how I'm going to express this then is I'm going to say, okay, if I've got a momentum, right? If I've got a momentum and my momentum is given by m times v, and I change the velocity of whatever the object that I'm looking at is moving at, if I change its velocity, then I'm changing its momentum, right? If momentum is made up of velocity and I change the velocity, then I'm changing the momentum. Okay, therefore, in physics, what we use, the symbol that we use to represent change is that triangle there. That's the triangle that we use. So what I'm essentially doing is I'm changing the momentum. So I'm going to say the change in momentum is equal to the mass of the object that I'm looking at times its change in velocity. I changed the object's velocity because it was moving at a specific velocity. The soccer ball was moving at a specific velocity. I kicked it to make it move faster. And when I kicked it, it moved faster, so it increased its velocity, so it changed its velocity. Since it changed its velocity, then it changed its momentum. Okay, hopefully that makes sense. Now, if I caused a change in the soccer ball's velocity, I changed its momentum. But what did I have to do in order to change the object's velocity? So going back to the soccer ball up there, what did I have to do to the ball in order to change its velocity, in order to make it move faster? I had to kick it, right? I had to kick it there. I had to kick it. Now, that kick to the ball is an external applied force, right? I'm going to call it Fnet. That's an external applied force. That's the force that is being experienced by the ball. Now, the ball could also be experiencing friction between it and the ground, and it could also be experiencing friction, but in this case we're just going to ignore friction. Okay, we're going to ignore friction and pretend as if the only force that this ball experienced is the Fnet from the kick of the person, right? So in other words, the Fnet here, the force that I applied by kicking the ball, the force that I applied on the ball by kicking the ball made the ball move faster, so the Fnet is not equal to 0. The force applied on the ball is not equal to 0, because if the Fnet was equal to 0, then by the law of conservation of momentum, our system would be isolated and therefore there would be no change in momentum. But in this case, we've got a change in momentum. If our momentum changes, it means it's not conserved. If it is not conserved, then it means our system is not isolated. Okay, so since our system is not isolated, there was a change in our system. Now, what caused that change? Well, what caused that change is Fnet. That's what caused that change, right? Now, what is Fnet? Fnet is the externally applied force on the object that caused the object's velocity to change. Now, from grade 11, right? What is the formula for Fnet? What does Newton's second law say about Fnet? Well, we'll remember that from grade 11, Fnet is equal to the mass of the object that we're looking at times its acceleration. Okay, now acceleration is key here, because if we go back to the ball, remember what happened to the ball. The ball had an initial velocity, right? It had an initial velocity, and then it changed its velocity. So the velocity from here to there changed. Now, what is a change in velocity? What is a rate of change in velocity? Well, the rate of change in velocity is acceleration. So acceleration is actually the rate of change in velocity. It's delta v over time. So it's the change in velocity over a specific period of time, right? Gonna go back to the ball again. There was a boy. It's me. Okay, this person kicked the ball, and then the foot of this person made contact with a ball for a specific period of time. So this foot applied a force on this ball for a specific period of time, right? That specific period of time caused a change in velocity. Now, that's the T there. So, right, that's the amount of time that the foot was in contact with the ball, right? So the rate of change in velocity, because the ball was moving at a certain velocity, it ended up with a certain velocity, and that change in velocity was caused by a force that was in contact with the ball for a specific period of time. Then we have acceleration, which is given by Newton's second law, which is Fnet is equal to m times a. Right, now, since acceleration is equal to the rate of change in velocity, we can clearly see that if we just replace that a with delta v over delta t, what we have is we've got F net, which is not equal to 0 because you have a change in momentum. Remember, F net is not equal to 0 if we have a change in momentum, right? So we've got mass times delta v over delta, that's a triangle, delta t. Okay, remember that this is from Newton's second law, and this is the same as acceleration. Why acceleration? Because acceleration is a rate of change in velocity. It's the extent at which your velocity changes. It gives us an indication of how much your velocity changes over a specific period of time. Okay, so this is just simply Newton's second law. Now, if you look at this, right, this is Newton's second law, but this entire equation here, if you look at that, we can take that delta t there at the bottom. Now, I'll tell you why we take that delta t at the bottom. Let me tell you now. Let's go back up there. Remember what I said here. Remember what I said up here. I said you have a soccer ball. The ball is moving at a certain velocity. You kick the ball changes its velocity. Hence, we have change in velocity, right? But since we have a change in velocity, and the velocity is what makes up momentum, is a part of what makes up momentum, then we've got a change in momentum as well. Because we've got a change in velocity. Since we've got a change in velocity, we've got a change in momentum. Now, if we've got a change in momentum, then it means the change in momentum is given by mass times change in velocity. Mass times change in velocity. Let's go back down to this equation here. What do you see here on top? We've got mass times change in velocity. This is exactly the same as this equation here. Mass times change in velocity. And we know that mass times change in velocity is equal to change in momentum. We can see it from this equation, right? So therefore, instead of writing from Newton's second law, instead of writing mass times change in velocity, I'm just going to replace that with change in momentum. Okay, I'm going to replace it with change in momentum. Let's do that right now. I'm going to replace it with change in momentum, and then what I have is F net is equal to mass times not mass times, because this entire thing is change in momentum. Then we've got change in momentum divided by change in time. Okay, remember all of this is from Newton's second law. Let me just write it a bit properly, closer to the equal sign. Change in momentum is equal to change in time. Okay, so what does this equation tell you? This equation essentially tells you that if you have a net applied force on an object, right? If you apply a force, if you've got a soccer ball and you kick it or you hit it, or if you've got a car and you push it, or if you've got a trolley and you push it, right? Whatever. If you cause movement on an object by applying a force on the object, then that object will experience a change in momentum over that specific period of time that you are applying that force onto it. Okay, I'll give you practical examples about that. Okay, so this is what this equation means. It means that if you have a net force, if you have a ball and you apply a force on that ball will accelerate and it will change in momentum. Now, the change in momentum happens over a specific period of time. Okay, so that's what this equation means. Now, if you rearrange this equation, if you say, okay, no, I don't want the rate of change in momentum, right? I don't want my momentum to be divided by t, because I just want to know my change in momentum. Never mind the amount of time over which it happened. I just want my change in momentum, right? Then what we do is we eliminate that t so that we have just our change in momentum on the right hand side. Okay, we eliminate our t. So how do we eliminate our t? Well, it's simple. We just multiply both sides by delta t. Multiply both sides by delta t. If we multiply both sides by delta t, what we have is f net times delta t, because we're multiplying both sides by delta t, is equal to delta p. That delta t and that delta t will cancel each other out, and this is what we have. This equation here is very important. This equation, we call it the equation of impulse. Okay, and impulse happens to be the net force multiplied by the time over which that force was applied, or the impulse is equal to the change in momentum of a body or of an object. Okay, so if there's anything that you should take away from this video, this is that the impulse of a body is equal to the change in momentum of that body, or the impulse of a body is equal to the net applied force on that body times the amount of time that the force was applied for, right? So let's put that into perspective. Let's give you a practical example of that. Okay, so that is what impulse is. And why is impulse important? Well, impulse is important because we like to reduce the amount of net force that is acting on an object. So the less force you have on an object in practical life situations, the better, right? The smaller the force, the better. But how do we make the force small, right? There's some instances where a bigger force is of benefit, but so I'll show you different examples where impulse is used, okay, where impulse is very useful. Okay, so let's say you've got a cricket, right? You've got a cricket, so you've got a bowler, right? You've got a bowler, person who's going to throw the ball, and you've got a batsman. So the batsman is there. Got a batsman with a helmet. There's your batsman there holding a bat. Okay, there's your, just gonna. Yes. Right. Okay, so now you're playing cricket. You've got this person holding a cricket ball. This person throws the cricket ball as hard and as quickly as he can to try to hit the wickets there. Right, to try to hit the wickets there, and then the batsman is trying to shield the wickets from the ball, right? So this bowler throws the ball towards the bat. This batsman hits the ball. They hit the ball, and you've got a fielder somewhere out there. I'm not sure if I'm using the correct words for these sports people, but you've got a person out there who has to catch this ball. Once the batsman has hit, this batsman has hit the ball, or the batter, I think they call them the batter. Once they hit the ball will go up into the sky and it'll move towards that person in the field there who has to catch the ball. Now, when this ball is very hard, okay, this ball is very hard, so it's quite painful to catch. Now, when this person catches this ball, remember this ball is very hard, it's moving very quickly. When this person catches the ball, you must pay attention when you watch cricket next time, or when you catch a ball yourself, a hard ball, right? What they'll do is, as the ball approaches their hands, they will sort of move their hands backwards as the ball is making contact with their hands. Okay, so if you look at me at the bottom left corner there of your screen, if the ball is coming, I'm looking at the ball, it's coming, and as soon as it touches my hand, I'm not going to catch it like this, right? I'm going to catch it like I'm going to move my hand back together with the ball, right? Because the more I move my hand along with the ball, the less painful it is to catch the ball, right? Even if you just take a ball, even if I don't use the analogy of cricket, just catching a ball in general, right? Just catching the ball in general, if you take a cricket ball and you throw it up, right? If you take a cricket ball or golf ball and you throw it up into the air and it comes back down at a very high pace, and then you have to catch it, the way you catch the ball is you start off, your hands start off looking like that, and then as the hand reaches your ball, your hands slowly move downwards, right? Slowly move downwards so that it is less painful to catch the ball. So your hands will end up at that position down there with the ball, right? Now, why do we do that? Why do we do that? Let me give you another example before I tell you why we do that. Let's say with a car, right? Most popular example that's given is with a car and a seat belt. Say the different parts of the car that I'm going to be looking at. I'm going to be looking at the front of a car, the bonnet of a car. I'm going to be looking at the airbags, and I'm going to be looking at the seat belt. Now, cars, the way they are designed, you'll notice that cars are designed like that, right? Cars are designed, the front end of a car is longer, is usually longer than the back end. It's longer, right? The front end of a car looks like that. Now, this is not just because it looks nice, right? There's a reason why it's a very important feature of a car, right? If you have this car and you are driving and you drive it towards a wall, right? Say the brakes say the brakes come loose or whatever, and then you can't stop the car, and then you're headed towards a wall at a very high speed, right? When you hit that wall there, your car will get damaged in the front, right? Your car will get damaged in the front. It'll bend like that in the front. Now, when it bends like that, you will notice that has some distance from the windscreen there, from the window there. Okay, so by design, that length there was made like that intentionally. Why was it made like that intentionally? It's so that we can reduce the force that is felt by the car from the wall. Okay, I'll explain how that works. That's why that's made longer there, so that the net force experienced by the car from the wall is as small as possible. I'll explain how that works, right? Another feature of the car is the airbag. Another feature of the car is the airbag, right? Another feature of the car is the airbag. So if you drive towards that wall, still the same car, you drive towards that wall, when you hit the wall, right, with that car, what's going to happen is that inside the car, the airbags will be deployed. Okay, the airbags, so there's your steering wheel there, the airbags will be deployed, and then whoever the person is inside the car will hit the airbag instead of the windscreen, right? But then this airbag, there's a reason why it's an airbag, because it can compress, right? It can compress, but we'll explain why. But also, I'm going to give you the reason now is the reason that we put in airbags in cars is so that we reduce the force felt by the person, right? The net force felt by the person. Okay, I'm going to explain with the equation how that works. All this is impulse. All these examples are from impulse. Okay, another example from a car is if you've got a car, same car, you've got a person inside the car, right? Person inside the car, and then this person is strapped on. They have their seat belt on, right? They have their seat belts on, and you've got a wall there. You've got a wall there, okay, and our wheels there, and then this car collides with the wall, right? If the person has their seat belt on, the person will still move forward when they collide, right? They will move forward, but they'll move forward at a much slower rate. They'll move forward at a much slower rate than they would have if they didn't have their seatbelt on. If they didn't have their seatbelt on, they were going to move forward very rapidly, very quickly. But now they're going to move forward very slower than they would have otherwise moved if they didn't have their seatbelt on. This is also very important, is to reduce the amount of force felt by the person, right? And this has to do with impulse as well, right? Now, what do all of these things have to do with impulse? Remember what I said impulse is? I said impulse is the net force on an object times the amount for which the net force was applied for. That is what impulse is, or it's the change in momentum. Okay, I'm going to focus on that part of the equation, Fnet times delta t. Let's go down there and write it out again and explain all these situations and why they are important. Now, if you've got Fnet times delta t, that's the left hand side of the equation, and this is what impulse is, right? Impulse is Fnet times delta t. Now let's start with the cricket ball example, or with the ball example, right? When the person standing here catches a ball, right, catches a hard ball, let's make it a bit smaller, looks like a soccer ball now. This is a cricket ball, right? This person will allow the ball to make contact with their hands, but as the ball makes contact with their hands, they will move their hands. They will move their hands in that direction away from the ball while the ball is touching their hands, right? You know how to catch a ball. As soon as the ball makes contact with your hand, you start moving your hand with the ball. You move your hand with the ball, right? As you move the hand with your ball, what happens? You are increasing the amount of time that it takes for the ball to come to a complete stop. You're increasing the total amount of time. So if you catch the ball like this, if you just put your hand like this and the ball comes and you just do that, now the ball came to a stop very rapidly, very quickly, meaning that the force applied by the ball on the hand was very, very small, right? It was very, very small. But that's not what you want to do, because the smaller the time that the force gets applied on your hand, the bigger the force. Now, why is that? Why does the force have to be big? Well, let me show you something. Let's stop talking about impulse for now and let's look at a bit of mathematics. Let's say I've got a change of momentum of 10, right? Let's say I've got delta p. Delta p is 10. Okay, we're still talking about impulse. Let's say delta p is 10, right? It's 10, and we know that delta p is given by F net times delta t. We know that this is one parameter, this is a second parameter, right? Now, these two things, when we multiply these two things together, we must get the number 10. Okay, easy enough, we must get the number 10. Now, which two numbers, when we multiply them together, can we get 10? There's plenty of numbers, right? We can say, let's say 2 times 5. Okay, can say 2 times 5. We can flip them around. We can say 5 times 2. We can say 10 times 1. We can say 1 times 10. Let's add one more. There's plenty. Even decimals, you can include decimals even. Let's include one decimal. You can say, or let's include two of them. Let's say you've got 20 times 0.5. Let's say 0.5 times 20. 0.5 times 20. Now, what do you notice here? All of these factors multiplied together give us 10, right? Each one of these give us 10. This is 10, that's 10, that's 10, that's 10, that's 10, and that is 10. Now, you will notice that, look at the left-hand side. Look at the left-hand side. The smaller the left-hand side is, the bigger the right-hand side will have to be between those factors, right? When the left-hand side is 2, the right-hand side, the delta t, is 5. Okay, cool, that's a bit big, right? But when I increase the left-hand side, when I increase the F net, then that one has to be smaller. So what is happening here? Let's look at this one as well, the next one. When this one is big, this one is 10, this one is 1. When this one is 1, this one is 10. So it looks like they're always trying to do the opposite of one another. When this one is 20, this one is 0.5. So when one is getting big, the other is getting small. So, right, it always seems like they're always trying to balance each other out. When one is getting bigger, the other is getting smaller. When one is getting smaller, the other is getting bigger. But all of them give me 10. All of them give me the same answer of 10. But in order for them to give me the same answer of 10, they sort of have to balance each other out so that when one gets bigger, the other one gets smaller so that we always get the same answer. This is exactly what impulse is doing, right? So here we're dealing with the force and we're dealing with the time. Now, if I can increase the time that the ball spends making contact with my hand, if I can increase the time that the ball takes to stop moving completely, then it means I can reduce the force that the ball is exerting on my hand. So my hand will feel less pain, right? I don't want my hand to feel pain when a ball strikes my hand. So what I'll do is I will try to increase the amount of time it takes for the ball to stop so that I reduce the amount of force that my hand feels so that I feel less pain. Okay, and this is why when I catch this ball, I move my hand together with the ball and I decide when to stop my hand so that I increase the amount of time it takes for the ball to stop moving so that it is less painful to catch it. Okay, so that is why we do that. Let's go to the car and demonstrate this further. With this car, right, before this car, so now you're driving this car, right? Now, before this car collides with that wall or crashes into that wall, what happens is that that car has been designed with that length there in the front and its front end. It's been designed with that length. Why is that length very important there? So if this car runs into this wall or crashes into that wall, it will take a certain amount of time for that part of the car to stop moving. It'll take a certain amount of time for that part of the car to stop moving. So the amount of time the car stops moving, that part of the car stops moving, increases. Now, because that amount of time increases, then what happens to the force that is felt by that part of the car? Well, it reduces. Remember, they're always trying to do the opposite of one another. When one increases, when the time increases, the force decreases. When the force increases, the time reduces, right? So what we're trying to do in these situations is that we are trying to elongate, we are trying to lengthen the amount of time spent moving in order to reduce, to minimize the force felt by the object that we're looking at. So that's why that part of the car is very important. That part of the car is very important so that when it hits the wall, when it collides with the wall, it bends. Now, as it's bending like that, as it's crumpling up, the amount of time it takes for this part of the car to stop moving increases. So therefore, that part of the car feels a lesser force than it was going to feel otherwise. So if the car looked like that, if it was completely flat and it ran into a wall, well, there is no time that's gonna be spent before the car comes to a complete stop, and then the force felt by this car was gonna be very much higher than the car up there, and the person inside was gonna be more injured than the person inside this car. Okay, so that is why that part is very important. It's to elongate the amount of time spent moving before the car comes to a stop. It's the same thing with airbags. Okay, with the airbag situation, airbags. This is the airbag that I tried to draw in there. What happens with the airbag is that here's the car there, right? Here's the person inside the car. There's the person inside the car. Now, when this car runs to when it heads towards the wall, right? Remember, I explained that part. So that part already we understand why it's there. Now, what happens with the airbag? The airbag gets deployed as soon as this car crashes into the wall, right? The airbag gets deployed. It comes out of its compartment, and the person sitting inside will make impact with the airbag. Now, the airbag is soft and mushy, right? It's not as soft as it's not that soft, but it's soft, right? It's soft. So the person will make impact with the airbag. Now, as this person is making impact with the airbag, the person will take a bit of time to stop moving before they completely stop moving. They'll take a bit of time, right? It will extend the amount of time that it takes for the person to stop moving. Now, because we've extended the amount of time that it takes the person to stop moving, we've reduced the amount of force, right? We've reduced the amount of force that the person feels. Now, because we reduced the amount of force that the person feels, then the person will be less likely to get injured. The person's likelihood of injury will reduce because the airbag increased the amount of time it took for the person to stop moving. Now, because the amount of time increased, what happens to the force? It reduces, it decreases, because the time and the force are always trying to balance each other out. They're always trying to do the opposite of one another. Remember when we looked at that mathematically, if the force gets smaller, the time gets bigger. If the time gets bigger, the force gets smaller. They're always trying to balance each other out, but they're always trying to give us the same value. Okay, so the 10 there was just an example. Same exact thing with the seat belt. Okay, so now we understand why that part of the car is important. We understand why the airbag is important. What about the seat belt? Same thing with the seat belt. Same exact thing with the seat belt. When the car approaches the wall, right, that part does its job, the airbag does its job, and the seat belt is also supposed to do its job. What does the seat belt do? Now, if a person is sitting inside a car and they are strapped on, they have a seat belt on, when the car makes contact with the wall, the seat belt increases the amount of time at which the person stops moving. When you have a seat belt on, you will move forward, right? When you hit the wall, you will move forward, but you will take a bit long. The time you take before you stop moving completely will be increased. Now, because we are increasing that time with the seat belt, what's going to happen? The force that you feel, the force that you experience from the crash will be reduced. And because the force has been reduced, then it means your likelihood of injury will also be reduced, right? And there's a bit of safety measure incorporated into that, and then you're less likely to be injured. Okay, so that's why the seatbelt is incorporated. It is incorporated in a car so that the time it takes for you to come to a complete standstill is increased. When time is increased, force is reduced. When force is reduced, the likelihood of you getting injured is reduced as well. Okay, and that is why the seatbelt is there. So the airbag, the bonnet, the front end of the car, and the seatbelt are all doing the same thing, right? They're doing the same thing. They have their own special features. They have their own special ways of doing these things, but they're all doing the same thing. They are increasing the amount of time it takes for you and the car to stop, right? This is increasing the amount it takes for the car to come to a standstill. The airbag and the seat belt are increasing the amount of time it takes for you to come to a standstill. It's all using the principle of impulse. Okay, so your momentum is changing, but the time it takes for your momentum to change is increased. Now, since the time is increased, the force is reduced. Since the force is reduced, you are safer. Right? It's the same exact thing. What I've just explained with the airbag, with the seat belt, with the car front end, and with the cricket ball, all of them are the same thing. Right? I can even give you one last example, one extra example. Let's say with the ball. Now, this is a situation where you want the time you spend making contact with the object to be reduced to be as little as possible. Say you've got a person, right? And this is a penalty now. Okay, this is a penalty. This is a soccer match, and then you've got a net there with a goalkeeper there, and then you've got a ball there. Now, this person wants to kick this ball as hard as possible so that it scores, right? This person wants to kick this ball as hard as possible so that it scores. Now, in order for this person to score, to kick this ball as hard as possible, what this person will have to do is they want to apply the maximum amount of force that they can. If they want to kick it as hard as possible, they want to apply an Fnet that is big. How do they apply an Fnet that is big? They kick it with their foot, right? They kick the ball with their foot, but they have to kick it as hard as possible. Now, if they want to make this Fnet very big, then what they will do is they will make sure that the amount of time their foot spends making contact with the ball is as little as possible. So that delta t, the amount of time their foot spends making contact with the ball, is as little as possible. Because if it is as little as possible, then the ball will move very quickly. You should try kicking a ball without by keeping your foot in contact with the ball for as long as possible. You'll see that the ball won't get very far, right? If you kick the ball and you try to keep your foot touching the ball won't get very far. It won't be a shot. It won't be a very powerful shot, right? But if you try to kick the ball, just kick the ball and make sure that you remove your foot from the ball as quickly as possible, then the ball will move quite some distance and then it'll have a very powerful shot. That is also that principle of momentum in action, right? We use this principle everywhere without even realizing it. So that is basically the principle of that's impulse, right? That is impulse. Trying to think if there's another example that I can use, but I think the examples that I gave make sense, and that is impulse. That is, so basically that is what impulse is, that is why impulse is important, and these are the equations given by given that describe impulse. Okay, so on a separate video we'll do examples. We'll answer some questions where we are tested on the principle, and we'll see if we can make sense of this principle further, right? Impulse and all of that. Okay, we'll see you in the next video. Till next time. Lesson number one, lesson